Our last descriptive statistic is the box and whisker plot. So the box and whisker plot is kind of between the detailed summaries that we have, so the frequency distributions and histograms, and single number summaries like means and standard deviations. So it's between them in the following sense. It provides a lot of the details that you get with a histogram, yet not all of the details, which make it very easy to compare across segments of a population, for example. So the beauty of a mean is it's very easy to compare across segments. You can say one segment has higher purchase intent than another. It's harder to do that with histograms, harder to do that with frequency distributions. While the box plot will provide a richer summary than just a mean or a standard deviation, yet still allow this sort of comparison. So I'm going to first tell you how to compute a box, how to interpret a box plot. Then I'll show you how to create one, both on paper as well as in SPSS. So the picture on page 57 is one of a box plot. Box plots are composed of three major parts. So the three parts are a box in the middle with a line through it. Then there are lines that extend from the box to what's called a whisker. That's the second part. The third part are outliers that lie beyond the whiskers. The box shows the quartiles. So the top of the box, maybe I can make this a little bit bigger. The top of the box shows the third quartile. So 75% of the data is less than the top of the box. The bottom of the box shows the first quartile. So the length of the box is therefore the interquartile range. It's saying what is the range of the middle half of the data. The line that goes through the middle of the box shows the median. So it's showing what is a typical value of this distribution. So again, think of the middle half of the data falling within the box. Let's move on to the second part of a box plot. So I said the second part was the whiskers. So the way to interpret a whisker is given off to the right. You should think that most of the distribution falls between the whiskers. So the whiskers will show the range of most of the data. So by most of the data, I mean everything but the outliers. And with box plots, there's a very specific definition of an outlier, which we'll get to in a minute. All right, good. Now let's, before getting into how to compute one of these, let's do a little example. And I think this example will show you how powerful these box plots are. Suppose that we have three segments of customers, segments A, B, and C. And then let's profile these segments based on their long-term value. So customer long-term value is a measure of how much that customer is worth to us in the future. So how much money do we expect to get from this relationship with a customer? More on that concept next quarter when you take the IMC class, IMC process class. Okay, so we have three box plots showing the different lifetime values. Let's discuss these. So first consider segment C. What you will see is that the box plot is very small. Now, the fact that it's so small indicates that this is a very homogeneous segment. So the length of the box is going to show dispersion. The interquartile range, well, it's a very small interquartile range relative to the others. The dot in the middle of the box here shows the median, and what you'll see is that these customers are typically much better than those in the other segments. So this is a group of customers with very high value that are pretty homogeneous. So it's a homogeneous group of customers with high value. The fact that the box plot is symmetrical, so the right-hand side looks like the left-hand side, indicates that it's a symmetrical distribution. So notice those first three characteristics, center, spread, and skewness, can all be assessed from a box plot. Let's contrast that with segment B. Segment B is quite different. So notice both the box is much longer, indicating a much greater interquartile range, as well as the whiskers. So these customers are very heterogeneous. Some are very weak. Some are extremely good customers, almost as good as those in segment C. So this is a very heterogeneous segment, almost too heterogeneous to be a segment, to be honest with you. Okay, so the spread is huge. The median is around sort of $50, a little bit less than $50. So that indicates the typical customer in this segment, not that there is a typical customer because it's so heterogeneous, but the middle of this distribution is around 45 or 50. Finally, this distribution is symmetrical because the right-hand side of the box and whisker plot is a mirrored image of the left-hand side. Let's turn our attention to segment A now. Segment A is very different from the other two. First off, the typical value of a customer is very low. So these customers are very poor. So half the customers have a value of sort of 5 or less. So that dots shows the median. Half of the distribution lies in that little window. The other half lies out here. So these customers are typically very poor. The distribution is more homogeneous than customer B, than segment B, but less homogeneous than segment A, and that's indicated by the length of the box and the distance between the whiskers. Finally, you're going to see some outliers here. So these outliers indicate that not all the customers in segment A are really weak. Some tend to be pretty mediocre. They're kind of in the middle of this entire range, but the vast majority of them are pretty weak. We can also note that this is a right skew distribution. We can deduce this from the fact that a very small percentage of half the data fall within this little window, the other half fall out here. Perhaps it would help to look at the sketch pad for a second. If I were to draw a box plot that is similar to that, so here is a box plot that is similar to the one that I have. Remember that half my distribution has to fall to the left of the median. So the distribution is going to look something like this. So we're already going to go down. And so that would be the corresponding histogram for such a box plot. All right, so that's how we interpret a set of box plots. Now, how do we actually compute one? If we go back to the previous slide, we have a little recipe here. Find the quartiles, find the ends of the box, and then plot the whiskers. I think it's easier to show how to compute one using a concrete example. So let's go back to that age distribution that we've looked at a couple times. This was on page 30. And actually, if we go 2 pages down, some of the key numbers are summarized for us. So the third quartile is 57, the median is 44, the first quartile is 34. So I'm going to go off to my notepad and let's sketch this. So I'm just going to take some notes. Q1 was 34, Q2 was 44, and Q3 is 57. The interquartile range is thus 57 minus 34, which is equal to 23. Now, let's go sketch this. I'm going to make this a value of 0, and we'll put this as the value 100. And let's create our axis. So let's call that 50. Here's 40. Here's 30, 20, and 10. And we'll write in all of our numbers. Now the first step is to create the box. So remember, the lower end of the box goes at the first quartile. So that's going to be at the value 34. The upper end of the box is at the upper quartile. So that is a value of 57. So we now have our box. The median is at 44, which is about here. And we're done with our box. That's the easy part. Now, to get the whisker, we're going to first go 1.5 interquartile ranges from the end of the box. So what is 1.5 times IQR? Where does 1.5 come from? Well, it's kind of arbitrary, to be honest with you. Tukey never really explains. Tukey, the guy who came up with box plots, never really explains it. But it captures this notion that most of the data will fall within the whiskers, as we'll see in a second. So 1.5 times 23 is equal to 34.5, pardon me. Let me fix that. So 34.5. We have to add 11.5 to 23. So what I said is we have to go 1.5 interquartile ranges from the end of the box. And that's going to be what I call a candidate whisker. So if we take 34 is the first quartile, minus 34.5, we get a minus 0.5. So I'm going to draw a little dotted line out here, which is at minus 0.5. Now, does it make any sense to have a whisker at minus 0.5? Remember, we're trying to capture the notion that most of the data should fall between the whiskers. Well, it doesn't make any sense because we have nobody in the sample who's minus 1/2 years old. Therefore, what we're going to do is take the smallest value that is greater than minus 1/2. So take the smallest value in this distribution that is greater than minus 1/2, and that happens to be the value 14. So 14 is the youngest person in this distribution. So I'm going to come over to here and draw a line. This is the real whisker at the value 14, showing the minimum. And there's no reason to put any outliers because there are no outliers. Now let's repeat the same thing for the other side of the distribution. If we take 57 plus 34.5, we get 91.5. So that is the value of my candidate whisker, is 91.5. Now, do we have any 91.5s in the data? The answer is we probably do. There are probably some 91.5-year-olds in this data, but nobody recorded 91.5. They recorded either 91 or 92. So since there are no 91.5s, that is not going to be my real whisker. We're going to take the largest value in the data set that's less than or equal to that. So the largest value is 91. My real whisker then falls at 91. So that is my whisker. Now we're going to see if there are any outliers, and yes there are. So there's 92 through 96. So we need to have some outliers at 92, 93, 94, 95, and 96. And we could label these if we wanted. For example, that's at 96. And that's our box plot. Now if you don't trust me, you can look at what the software does. And that's given 2 pages away at the lower end, and you will see exactly the box plot that we just generated. So let's go back to page 57, and so